Hi everyone, welcome back. Today we will start a new lesson. Chapter 6 of class 12, Electromagnetic Induction. In the previous chapter, we learned what is magnetic flux. What is magnetic flux? It is a total number of lines of force passing normally through a surface is called magnetic flux. When you take a bar magnet, around the bar magnet, there will be magnetic field and there will be magnetic flux. Okay. Today, we first discuss Faraday's law of electromagnetic induction. So, we will discuss 3 experiments done by Michael Faraday. Okay. Faraday's experiments on electromagnetic induction. So Faraday, he used a coil and a bar magnet in his first experiment. First experiment. He took a coil. This is a coil. We can also call it as a solenoid. It is a coil. The coil is connected to a galvanometer. You know what is the purpose of a galvanometer? To detect current. So the coil is connected to a galvanometer. And he took a bar magnet also. This is a bar magnet. North and south poles I marked. You know, surrounding the bar magnet, magnetic field lines are there. Okay. So magnetic field lines, these are the magnetic field lines. You know, magnetic field lines start from north and then move towards south and then inside south to north. That all you know. Now, he moved the bar magnet into the coil and he observed a deflection in the galvanometer. He observed that the galvanometer is deflecting towards left. Okay, this is first experiment. So he moved the bar magnet into the coil. What happened? Galvanometer showed a momentary deflection. It deflected towards right side. Okay. This shows that galvanometer deflects because there is a current is produced. This current is known as induced current. We say a current is induced. There is no physical contact between bar magnet and the coil. He just moved the bar magnet into the coil or towards the coil. What happens? Current is induced. Galvanometer deflect towards right side. Okay. Move the bar magnet towards the coil. What you observed? Galvanometer deflected. Towards right. Now he moved the bar magnet away from it. Then what is happening? Then he observed that galvanometer deflected in opposite direction. Okay. He moved the Faraday moved the bar magnet away from the coil. What happened? The galvanometer showed opposite deflection. Galvanometer showed opposite deflection. What is the meaning of that? Galvanometer showed opposite deflection means current is reversed, right? Current flows in the opposite direction. Induced current is moved in opposite direction through the coil. Now, he moved the magnet, he kept the bar magnet stationary inside the coil. Then he did not observe any current. Galvanometer was not deflecting. Okay? He kept the bar magnet, stationary inside the coil. No current is observed. So, to get a current in the coil, he has to do some movement. He has to move the bar magnet, or he can move the coil towards the bar magnet. Whenever there must be a relative motion. Okay. So when there is relative motion between the coil and bar magnet, what happens? Current is induced. And what is happening when you are moving? You know, when you are moving the bar magnet towards the coil, magnetic field inside the coil increase, or magnetic flux increase. Coil has an area, so there will be magnetic flux. So when you move the bar magnet towards the coil, magnetic flux through it increases. Similarly, when you move away, what happens? The magnetic flux through the coil decreases. When you move the bar magnet away, magnetic field and magnetic flux through the coil decreases. If you keep the bar magnet inside the coil stationary, there is magnetic flux and magnetic field inside, but it is not changing. Okay, when you are moving, whenever there is relative motion between bar magnet and the coil, this magnetic field and magnetic flux is changing. Then only current is induced. If you keep the bar magnet inside the coil, magnetic flux is there, magnetic field also there, but magnetic field is there, hence flux will be there, but there won't be current induced. So what is the condition for current to be induced? The magnetic flux must change. Magnetic flux linked with the circuit should change. Then only current is induced. Okay. This is the first experiment by Faraday. Now, second experiment. In second experiment, he used two coils. See, this is one coil. This coil is connected to a battery and a switch. And another coil, it is connected to a galvanometer. You know, when the coil solenoid or coil is connected to a battery, when current is passed, it acts as a bar magnet, you know. It acts as a bar magnet. Okay. It acts as a bar magnet. So if you move this coil, first coil, towards or away from the second coil, you can see a galvanometer in the second coil is deflecting. So the first coil here act as a bar magnet, right? When it is moved away or towards the second coil, magnetic field and hence magnetic flux through this coil changes. Then only magnetic induced current is developed. If you keep the first coil stationary, there will be magnetic field passing through the second coil, but it is not changing. Okay, when there is relative motion, magnetic field and flux is changing, and then only current is induced. Okay. Somehow magnetic flux must be changed. That is the thing. Okay. Now, third experiment. Here, he took a soft iron core. This is a soft iron core. He connected a coil here, coil 1. The coil is connected to a battery or a cell and a key. There is a second coil here, wound over the same soft iron core. This is connected to a galvanometer. Now he closed the switch. You know, when the switch is closed, current through the first coil starts increasing. After some time, it becomes constant. So during that time, the current through the coil is increasing. That time, magnetic field through the first coil changes, and this magnetic flux will reach the second coil through the soft iron core. You know, soft iron core can permit magnetic field. That is a specialty of soft iron core. So when circuit is closed, what will happen? Current through the first coil increases. So magnetic field through the first coil changes. That magnetic field and flux is linked with the second coil through the soft iron core. So magnetic flux linked with the second coil changes. So you can see a current induced. Okay. Now he opened the key in the first coil. First he closed. So you can see that current is changing. So magnetic field is changing for a small time. So that magnetic flux come to the second coil. So the galvanometer showed a momentary deflection. Because the magnetic flux change is there till the current in the first coil become maximum. It will take a small time only. So during that time only magnetic flux linked with the second coil changes and it shows a momentary deflection. Now he opened the switch. Then current through the circuit first coil decreases and becomes zero. It will take a small time for this process. During that time, magnetic flux changes with the first coil that will be passed to the second coil by the soft iron core. You can see a momentary deflection in the galvanometer in opposite direction. Okay. So induced current is in opposite direction. So here also, what is the conclusion here? From all the three cases, we can conclude that to produce induced current, the magnetic flux linked with the circuit or the coil must change. Somehow it must be changing. Okay. In the first two experiment, change is by relative motion. In the third case, relative motion was not there. Only changing the current in the first coil has produced a change in magnetic flux. So these are the Faraday's experiment on electromagnetic induction. So what is the conclusion here? Whenever the magnetic flux linked with a coil or a circuit changes, a current is induced in it. And this induced current lasts as long as the change in flux takes place. Okay, this is the conclusion. So what was the conclusion of Faraday's experiment? Whenever the magnetic flux linked with a coil or a circuit changes, an EMF is induced in it. Okay? An induced EMF or current lasts as long as change in magnetic flux take place. This was the conclusion of Faraday's experiment. So see, he made 3 experiments. First experiment, he moved the bar magnet for changing magnetic flux into the coil. So current induced by a bar magnet. Second case, he moved a current carrying solenoid to another solenoid. So current is induced by a current only, because first coil was a current carrying coil. Third case, without relative motion, change in magnetic flux is produced. So anyway, for production of induced EMF or current, the magnetic flux linked with the coil must change. Then only induced current is developed. And this phenomenon is known as electromagnetic induction. So what is electromagnetic induction? It is the phenomenon of production of an induced EMF or a current in a circuit whenever the magnetic flux linked with it changes. Okay, this is electromagnetic induction. The phenomenon of production of an induced EMF or current in a coil or circuit when magnetic flux linked with it changes is called electromagnetic induction. Is called electromagnetic induction. The phenomenon of production of an induced EMF or current in a coil or circuit when magnetic flux linked with it changes is called electromagnetic induction. Okay. So producing induced EMF or current, magnetic flux must change. Now we are coming to Faraday's law of electromagnetic induction. Okay, Faraday's laws of electromagnetic induction. So one is whenever magnetic flux linked with a circuit or coil changes, an induced EMF is developed in it. And the induced EMF lasts as long as change in flux take place. Whenever the magnetic flux linked with a circuit or coil changes, current is induced in it. And induced current or EMF lasts as long as change in magnetic flux take place. Now, second law, the magnitude of induced EMF is equal to the time rate of change of magnetic flux. The magnitude of induced EMF is equal to rate of change of magnetic flux. See, we can write E is equal to minus d phi by dt. Phi is the magnetic flux. E equals minus d phi by dt. See, there is a negative sign. This negative sign shows that the induced EMF has an opposing nature that I explained as the next law. Okay, the induced EMF has an opposing nature. That is the meaning of that negative sign. It opposes the cause which produced it. Okay, so these are Faraday's laws of electromagnetic induction. So what are the Faraday's laws of electromagnetic induction? Whenever magnetic flux linked with a circuit or coil changes, current is induced in it. And current lasts as long as the change in magnetic flux takes place. What is the second law? That is very important. The magnitude of induced EMF is equal to the time rate of change of magnetic flux. E is equal to minus d phi by dt. There is a negative sign. It shows that the induced current or an EMF has an opposing nature. This is Faraday's laws of electromagnetic induction. And there is a rule to find out the direction of induced current. We can use Fleming's right-hand rule or right-hand thumb rule that we will discuss later. Okay. Now, another important law is Lenz's law. Lenz's, another scientist name, Lenz's law. Okay. Lenz's law. See, in the Faraday's law of electromagnetic induction, there was a negative sign. Negative sign. I told you negative sign shows that there is an opposing nature for the induced EMF. It is given, the explanation of negative sign is given by Lenz's law. Lenz's law states that the induced EMF, the direction of induced EMF is such that it opposes the cause which produced it. See, you know, in the Faraday's first experiment, we moved the bar magnet into the coil. Then in the coil, induced EMF is produced. That EMF will oppose the movement. That means when you are moving the bar magnet towards the coil, induced current in the coil flows such a way that the bar magnet is repelled away. Okay, while moving bar magnet towards the coil, magnetic flux through it increases. So induced EMF try to push away the bar magnet. Okay. In other way, when the bar magnet is moved into the coil, magnetic flux through the coil increase. So induced EMF try to decrease the magnetic flux. When you are moving, magnetic flux through the coil increase. So induced EMF try to decrease that flux. That is why it is repelled away. Okay, this is Lenz's law. So what is Lenz's law? Lenz's law states that the induced EMF flows in such a way that it always opposes the cause which produced it, right? So Lenz's law states that the direction of the induced EMF is such that it opposes the cause that produced it. That produced it. So induced EMF always opposes that produced it. Opposes the cause that produced the induced EMF. This is Lenz's law. This is why the negative sign in the Faraday's first law came. So we can find out the direction of the induced EMF by applying Lenz's law, or another law, Fleming's right-hand rule. Either of these rule can be used to find out the direction of induced current. Okay. See, listen. See, this was the coil, right? When you move the bar magnet north and south, so what will, when you moved in this way, so magnetic flux through the coil increase, right? When you move the bar magnet towards the coil, magnetic flux through the coil increase. So induced EMF is developed. It will opposite. That means induced current will flow here in the anti-clockwise direction, making this end as north pole. So north pole will repel the north pole of the bar magnet. So direction of induced current here is, when you look from the side, direction of current is anti-clockwise, like this. Okay. Now, if you move the bar magnet away, what will happen? Flux through the coil decreases. So induced current flows such that this end becomes south pole. Then south will attract the north. The bar magnet will be attracted, right? So induced current is always opposing the cause which produced it. If induced EMF is due to increase of magnetic flux, induced EMF try to decrease that one. Okay, this is Lenz's law. Always you remember this clock rule. See, this is a circular coil. If the current is in this direction, clockwise, that means magnetic field will be into the plane of the paper, into it. This represents a south pole. Always remember, if current is in the clockwise direction, this loop, this phase will be south pole. So magnetic field will be into, like this. We represent magnetic field into, right? The opposite side will be north pole. And if the current is in anti-clockwise in a coil, this way, that will represent a north pole. North pole means magnetic field lines will be out of the plane of the paper, right? Magnetic field will be out. From north pole, magnetic field lines coming out, you know. For south pole, magnetic field is moving into, right? This is the rule for determining the poles, whether south or north for a coil. Okay, this you should keep in mind when applying Lenz's law. So here, when north pole of the bar magnet is moved towards the coil, magnetic field through the coil increase. According to Lenz's law, the induced current should decrease that increase of flux. So what will happen? Induced current move in what direction? North pole, in the clockwise direction, anti-clockwise direction. That is why this become a north pole. The north will repel away the bar magnet. Okay. In the same way, this is the coil. In the same way, this is the coil. Okay, galvanometer. There is a bar magnet here, north and south. Suppose this bar magnet is moved away. Bar magnet is moved away. Then what will happen? Flux through this coil decrease. So induced current developed in the coil try to increase the flux. By moving away, flux is decreased through the coil. So induced current try to increase it. So what will do? This induced current flows in clockwise direction here. So clockwise direction means current should be in the clockwise, in this way, clockwise. So this becomes south pole. So south pole attract the north pole. So magnet is attracted back. This is how we determine the direction of the induced EMF. Okay. And Lenz's law is not violating law of conservation of energy. See, in the first diagram, I told you when the bar magnet is moved towards the coil, because of induced EMF, the end of the coil near the north pole become another north pole. So repulsion, right? So you feel a repulsive force when the bar magnet is moved into the coil. Because of induced EMF, this repulsion comes, right? You have to do work against it. So this mechanical work done is converted into electrical energy. Similarly, from the second diagram, when you move the north pole of the bar magnet away, induced current make the end of the coil near to the north pole a south pole. So it will attract it. Again, you have to overcome that attractive force. You have to do the mechanical work. External agency have to do the mechanical work. This mechanical work is converted into electrical energy. So only energy transformation taken place. No energy is not created or not destroyed. So Lenz's law is in accordance with the law of conservation of energy. Okay, everyone. Thank you for watching. Keep on watching. Make your physics strong. Thank you, everyone. Goodbye.